but it looks like my, there we go, okay. But I'm actually going to be showing some new stuff that I've been working on at my postdoc, and it's actually really fun to be in this session because, as Jack just mentioned, this is a really great time to be thinking about exploring the far side. This is my my initial endeavor into studying far side. Primarily, I focus on impact cratering on the lunar far side, but I promise to those of you who've seen me talk before, there are no crater counts in this talk, none of those. So I hope that that you'll enjoy the rest of it. So we've heard from a lot of people here, both in the presentations today and over the past couple days and in posters, that the South Pole-Aitken Basin is a high priority target for exploration and sample return because of the many scientific objectives that can be addressed. And for example, solar system bombardment history is the first science concept outlined in the scientific context for the exploration of the moon. In addition to investigating the lunar interior, impact processes, volcanic evolution, and regolith processes, all of that can be accomplished by studying different locations, sometimes single locations, in the South Pole-Aitken Basin. And in particular, all of these different tracks and questions feed into revealing planetary processes through time and give us more information about the solar system evolution. Now, a few things we know, very basic. We've heard a lot about this already, that South Pole-Aitken is the oldest lunar basin, but we don't have an absolute age date for it yet. It likely excavated mantle materials, but it's since been heavily modified by impacts and volcanism, and that's no surprise because it is so old. It's very geologically complex, and therefore efforts to map it are very difficult. Now, on the right are two figures from some earlier papers, and absolutely do not represent the huge amount of literature that have gone into investigating the geologic units in South Pole-Aitken, but we have Mare deposits mapped in an area of South Pole-Aitken. And then also here from Peters et al. 2001, we have confirmed basaltic deposits in black. We have intrinsically basaltic deposits in this gray color, and there are a couple of those clustered here. And then I've gone and modified this figure to show in red here the likely pyroclastic deposits that were identified on the basis of multispectral data. Now, additionally, and I think that all of us in this room will agree that the recent spacecraft data returned by multiple missions, multiple instruments, enabled further characterization of the geologic units in SPA by allowing a combination of approaches and the for, in some cases, the first time being able to use multiple data sets to inform us about the geology. Now, for the remainder of this presentation, I'm actually going to be talking about some looks into topographic roughness to look at smooth plains deposits as an approach toward teasing out what is impact melt versus volcanic versus basin ejecta, for example. And in 2013, Nisha and co-authors created roughness maps from LOLA data. And here's a figure showing a number of craters, Tycho and Copernicus, for example. And the relative brightness here represents the roughness. So these are all stretched to the same scale, and bright materials are rough, and darker materials are smooth at this 115-meter baseline. And for the remainder of the presentation, I'll be showing images at 3 different of the baselines that they calculated. Now, this is absolutely not the first and won't be the last investigation that looks at roughness. Rosenberg et al. In 2011 used LOLA data to determine a range of parameters related to surface roughness. So this is one of many, but as I was starting to do the work on this, I got interested in this measure of roughness. Now, so that we can get an idea of what we're looking at when we go to this really messy area of SPA, here again I'm showing relative roughness, where brighter is rougher and darker is smoother. And we have Imbrium Basin, and on the left we have the 1.8 kilometer baseline, and the majority of the Mare materials are very smooth. You don't really see a lot of expression by what we know are wrinkle ridges there. However, the Imbrium Basin rim and Copernicus and Plato up here are pretty distinct. Now, as we get to smaller and smaller baselines, the approximately half-kilometer baseline, we start to see more the finer scale roughness. So we begin to see some of the ejecta materials from Copernicus here, as well as some of the tectonic deformation and also Aristotelis ejecta. Now, going to the 100-meter or so baseline, the smoothness of the Mare deposits absolutely disappear, and we see crisscrossing of crater ejecta and tectonic deformation. So now taking a look at Tycho, again, the large to small baseline, we can get an idea of how the different surface features are going to be showing up in this roughness data. So we have pretty much very, very rough at this fine scale, and we do see some smooth deposits representative of the impact melt in Tycho in that left image. Now, looking at the Schickard cryptomare, this ancient mare that Jenny briefly discussed the other day, here we have an L-rock whack that is showing this this fill here, and the cryptomare is right around there. And we see that this deposit is very smooth in this 1.8 kilometer baseline, but essentially disappears in this 100-meter or so baseline. So we can get an idea of what we're going to be looking at here in this region of SPA, kind of surrounding the southwestern area around Apollo. And I want to draw your attention particularly to Apollo Basin, where we know there are Mare deposits, and then also here to Finsen, which is one of the youngest craters. Now, Wilhelms and others suggest that based on stratigraphy, Finsen is Eratosthenian in age. So we know that compared to everything else, it probably is going to be the roughest at multiple scales. So we've got a quick view here of all three, and then I'm going to walk through these three roughness maps at the full screen scale. So we have Finsen here and then Apollo Basin, and it's not very pretty when we're scrunching it down here. So we're just paying attention here to the fact that we are seeing smooth deposits in period craters and also in this kind of intercrater area. As we get to the smaller baselines, however, some of these deposits, for example, the Mare fill in Apollo, are disappearing, but we do see some smooth deposits coming out. We also are seeing evidence of crater ejecta from Jackson. Now, stepping through some of the roughness again so that we can focus a little bit on the detail, in this image, Finsen here has the roughest crater rim relative to the remainder of craters and geology in this area. And I think that lends really good evidence to the fact that Finsen is young. And as we step through to the 100-meter baseline, we'll see that it becomes very, very bright. But we do see that there is a smooth deposit in there. And we see smooth deposits in Bose and in these other craters as well. And so perhaps this roughness can give us an idea of what are Mare versus impact melt, what is old Mare, really old Mare, versus maybe old impact melt. And that's something that I particularly think is interesting. So now we're at this 0.46 kilometer baseline of roughness, and some of these deposits down here in Bose and Baba have disappeared compared to the smooth deposits still remaining in Apollo and Finson, again, is starting to become very, very bright relative to everything else. We're starting to see evidence of some ejecta thrown and superposed in this area. And we even are beginning to see the tectonic deformation here in Oppenheimer. And again, looking at this 115-meter baseline roughness derived from LOLA, we see that virtually all of these Mare patches are disappearing in this area. However, we do see evidence for some smooth deposits, and there seems to be a little bit left in Finson. But again, Finson is super, super rough compared to the remainder of these other craters, which for the most part are really not much older than Finson. And this ejecta, I think, from Jackson is just really striking because it really doesn't show up that well in the morphology mosaic that I showed, partly due to the solar illumination, but also because this is really picking up that fine scale roughness. Now, I promised you that I'd show impact melt. These are my last couple of slides. Here's Finson in the WAC mosaic. Scale bar here is 20 meters or so. And if you took a cutout of this smooth material, although some might argue that it's a bit more hummocky up toward this northern part of the rim, this is classic morphology of impact melt deposits. You could say take this cutout, overlay it on some of the floor material on Tycho or King Crater, even perhaps some of the regions in Copernicus, and you'd be able to fool many people. And in addition, not only is the smoothness and relative crispness of this deposit very telling to me, but you also have smoothing of the landscape surrounding the crater by perhaps impact melt veneer, and then we even have some ponded deposits over here, which granted could be Mare deposits or basin ejecta. However, the fact that there's only one or two impact craters of a resolvable size at this resolution really lends itself to an impact melt origin. And I just zoomed in a little bit here. I don't know whether you can see this on the projector. It might be visible on those television screens, that there are some tectonic cracks here, perhaps due to cooling. We see that all the time in Copernican and Eratosthenian aged craters on the near side and in other regions of the far side, non-SPA. And when you take a look at the NAC view, and I don't have NAC images to show you here, there are impact craters hundreds of meters in diameter that punch through this material and expose boulders. So whatever regolith layer is on this material is not very thick at all. So in conclusion, I did show you impact melt. So if you read the abstract and that's what you are sitting here to listen to, I hope that I made you happy. We all can agree that recent data sets enable new looks at persisting and sometimes old questions and allow investigations and promote investigations that benefit from or indeed require the use of multiple data sets. A lot of the work that's been presented at this meeting so far really shows, I think, the wonderful result of melding multiple data sets that we would not be able to do without LRO and M-cubed and other data sets. Now, the LOLA-derived surface roughness at the different baselines absolutely emphasizes the diversity of plains and SPA. That's no big surprise. We know from previous work that that's the case. But it also gives us a bit new insight, and maybe we can look at an approach using the roughness and other data sets. So in conclusion, I have a lot more new questions and answers to tell you today. Of particular interest to me is what should old plains look like compared to younger plains in SPA and elsewhere, and how do old impact melts differ from old Mare? I really love looking at impact melts. And the fact that Clive brought up a good question yesterday about what old impact melts versus old Mare look like, that's not something that we've been able to study before. So with all of these data sets and others, we can start to go after some of these remaining questions. So with that, I thank you.
think one thing to keep in mind in terms of old versus more recent melts is that the one thing that we found is that the water undergoes chemical weathering in and of itself. And so that's going to actually change the chemical composition over time. I think that that's a really important question going forward because it would allow, sample returns could provide some more concrete data on this.
Absolutely. I've done some work investigating recent impact melts. I looked at a couple areas on the moon and identified what I interpreted to be Copernican and Eratosthenian as a baseline of this is what impact melt should look like, with the goal during my postdoc of expanding that to a global survey and then also trying to tease out some of the older infilled craters with that. But that's something that's like the next step. So thank you.
Okay, so we're running behind.
Yep. Thanks, Sam.
Our next speaker is Dr. Neal, who's going to